Hi, welcome back. In this video, we're going to talk about symmetry and dilations. As our last topic of the unit, so far we have done a rotation, a reflection, or a translation. Now we're going to talk about as a different form of transformation. We're going to first identify what type of symmetry an image has, if it's symmetrical, and then a dilation as a change, as an increase in size or a smaller change in size. So let's get to it. As you can see here, we have three different types of symmetry. The most basic symmetry, which we probably already know, is line symmetry, when I can draw a vertical or horizontal line and the image basically reflects about itself. Is the image symmetrical about a line? Can I fold this onto itself and form the same image, right? Point symmetry is referring to putting a point on the center of the image, and can I rotate it 180 degrees? So basically, can I flip it upside down, rotate it 180 degrees, and get the exact same image? As you can see with the end, it would work out. Rotational symmetry happens when I can rotate about at any degree, including 180. So can I rotate it at 60 degrees, 40 degrees, any degree format less than 360 to get the exact same image? And as you can see here, if I draw all these symmetrical lines that I have, this is going to rotate every 45 degrees. So every 45 degrees, I get the exact same image. We call that rotational symmetry. So let's try a few examples and let's see if we can identify the components. Feel free to pause this video and try them yourself. Feel free to check to see if you can identify whether these four images have line, point, or rotational symmetry. So as you can see here with this hexagon on the left, I can draw a vertical line and reflect the image about itself. So it has linear symmetry. I can rotate this image 180 degrees, and I can also have the same image, which is point symmetry. Now, since it has point symmetry, by default it will have rotational symmetry. But as you can see, this image will be reflected every 60 degrees. I'm going to end up getting the same image, which is why it's also rotational symmetry. The A in the bottom left, as you can see, has also a vertical line that can reflect about itself. So we have linear symmetry. It doesn't have point symmetry because if I reflect it 180 degrees, it'll just be an upside down A, right? And that's not the same image. And it does not have rotational symmetry because it would have to flip all the way to 360 degrees before the image repeats itself. So this one only has linear symmetry. On the right-hand corner, I do not have linear symmetry because vertically or horizontally I cannot flip the image onto itself. But I do have point symmetry because if I rotate this 180 degrees, I would get this top part would become in the bottom portion, right? Every 180 degrees, I would have the exact image. So that gives me point symmetry and by default, rotational symmetry. Lastly, as you can see in this bottom right-hand corner, this sort of looks like a Mitsubishi car symbol. It does have linear symmetry because I can flip this onto itself. I do not have, though, point symmetry, because if I rotate this 180 degrees, I would basically have something like this, right? And it's not the identical image. But since it does not have point symmetry, will it have rotational symmetry? Well, if I rotate this image, right, 120 degrees, this piece will get repeated down here. And if I rotate that 120 degrees, this image will get rotated over here. So yeah, every 120 degrees, this has a rotational symmetry. Now let's talk about dilations. A dilation, this component or part of the video will be more of a review from our Unit 5. when we spoke about scale factors, when we spoke about ratios and proportions. So, a dilation about a coordinate plane is really referring to when I draw an image. Let's say we have a triangle. I'm looking at how far is each point from the origin. And I'm going to take that distance and I'm going to multiply it by some scale factor. We'll call it k. Sometimes they call it r. K also works. It's really just multiplying it by some sort of value. And then we're going to double that distance or triple that distance or multiply it by some number to get a new location. So if I have the coordinate, I just really need to multiply my scale factor, take the y component, multiply by my scale factor, and I should have the new coordinates of that dilation. Now, depending on what that scale factor is, if that scale factor is bigger than 1, the image is going to increase. And that makes sense, right? If you think about it, if I multiply something times 2, it'll double in size. We'll have an enlargement. If I multiply it by something less than 1, between 0 and 1, like 1/4 or 1/2, we're going to have a reduction because you're going to change the picture to smaller its size. So let's try a few examples, and then we'll talk about here in the end, how do you find the scale factor? So here we're given the scale factor as k equals 2. So I already know, since it's bigger than 1, it's going to be an enlargement. This parallelogram is going to double in size. Let's highlight this x-axis and y-axis a little bit so we can count the values a little better. I'm going to first identify the points. M is located at -1, +3. N is originally located at 1, +4. O is located at -2, -1. And P is located at -4, -2. All I really have to do is multiply everything by that scale factor. So I'm going to multiply everything times 2. -1 times 2 is -2. 3 times 2 is 6. 1 times 2 is 2. 4 times 2 is 8. -2 times 2 is -4. -1 times 2 is -2. -4 times 2 is -8. -2 times 2 is -4. As I plot these points, you'll see that -1, 3 turns into -2, 6. This is my new m value. N is located now at 2, 8. This is now n. If I look at O, -4, -2, this is now the location of O prime. And -8, -4 comes down to right here, P prime. Notice how this image is twice the size. If I actually went about finding, like say, the distance between these points, M and N, using the distance formula or something, I can compare those two lengths, and I can see how they are doubled in size. Right? So everything here is doubling. The lengths, the location of the points, everything is times 2. Notice here how k is 1/4. So since that value is less than 1, I know that this picture is going to reduce in size. This trapezoid, FGHI, is going to shrink to a smaller size, 4 times the size actually. So let's try it. The location of F is -2, 8. The location of G is +4, 8. The location of H is +8, -4. The location of I is -6, -4. All we're really doing here is we're going to multiply every number times 1/4. So if you're not so good with fractions, feel free to grab a calculator so you can multiply it. You can also do these by hand, right? -2 times 1/4 would mean this is -2/1. You multiply fractions sideways. This gives you -2/4, which simplifies them to -1/2. Or in the calculator, -2 times 1/4 is still -1/2. 8 times 1/4 gives me 2. 4 times 1/4 gives me 1. 8 times 1/4 gives me 2. 8 times 1/4 is 2 again. We have a negative 1. Negative 6 times 1/4, let's try that over here, gives me negative 6/4, which comes down to negative 3/2, or negative 1.5. And then negative 4 times 1/4 is negative 1. When I plot these points, I can see negative 1/2 and 2 is here, f prime. 1, 2 is g prime. 2, negative 1 is h prime, and I prime is at negative 1.5, comma negative 1. Notice how this trapezoid shrunk by 1/4, or 4 times smaller. You can also look at it as the distance from here to the origin and from here to the origin is 1/4 that length. So now let's talk about how do you find the scale factor. So far we were given the scale factor and we were supposed to find the new image, right? So we use the scale factor to find the new image. If we want to go backwards, we want to create a formula, right? For scale factor, the general formula would be the new image divided by the old image, or the original image, or A prime over A, the location, right, over the other one. So, as you can see here, triangle ABC is mapping onto XYZ. So, the original one is the blue picture, and XYZ, the new one, is the green one. So we're going from blue to green, which means I'm looking for a value that's going to be less than 1, since it's going to be a reduction. So pick a side. One way to do this is choose a side that we're looking at. Horizontally, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is the length, the distance from A to C. And then over here, I can look at 1, 2, 3, 4, 5, 6 is the horizontal length as well. So since we're doing new over old, our scale factor would be new over old, where the new image is 6 and the old image is 9. And that simplifies down to 2/3. Now, I can also do this vertically, right? I can count these units divided by this units. I can do it diagonally, but to find diagonal distance, I would do Pythagorean theorem or like the distance formula. So it's probably easier if we just stick to the diagonal points, the horizontal points versus the diagonal ones. Another way to do this is you can actually look at a coordinate point. I can look at location of A versus location of X. A is located at -7, or 1, 2, 3, 4, 5, 6, sorry. -6, -3. And X is located at 1, 2, 3, 4, -2. And you can use the points as well to do that, right? I can see how the ratio of the new image over the old image, right? -4 over -6. Or -2 and -3. The scale factor for both, when I reduce it in size, is still 2/3. So you can use the points to identify the scale factor, or you can use an actual distance, as long as you have the new image divided by the old image. As you can see here, when we're trying to identify the scale factor as our last example, notice how we have our new image is K prime. The distance to the origin would be 2 units. And then the new image, the original image, is 5 units away. So I can tell the difference between new and original, or new versus old, based on the prime value, right? K to K prime. So we have new over old, or new over original for our scale factor. The new one is 2. The original one is 5. I can simplify that fraction smaller, so as you can see, the scale factor is 2/5, which is about 0.4. And 0.4 is definitely less than 1, which is why our original image is going through a reduction, because it's reducing in size. Alright guys, let me know if you have any questions. I hope this video has helped. Don't forget to like and subscribe. And as always, we'll calculate later.